Oops, where's my set? Damn it. Sorry, technical difficulties. Alrighty. Oops, turn this off too. Well, welcome back, everybody. Oh, can I get a thumbs up or something from somebody who can hear me to make sure this is actually working? Yes, okay, thank you, Benjamin. All right, well, guess what? This is our last week. So if you can survive just a few more days, then we will have successfully reached the end of a semester with Zoom. And well, I hope it's our last one. Do you guys have any comments or questions about the material we were doing at the end of last week? So we're doing Green's theorem now. This is a cool and very interesting theorem about integrals. Did you try the homework exercises, and do you have any difficulties with those? Malik, yes, your hand is up.
Oh, I just had a question on Green's theorem.
Okay.
So like, what would you say is like the main idea or like the practical like application of this? Like,
we're going to do some more applications. I did give you one at the end of the hour on Friday, which is that it kind of counterintuitively, it can tell you the region of the area of a region from just knowing how to get around the boundary of that region. So, you know, we're actually going to do more analogs of that in higher dimensions too. You could imagine, since nobody wants to go into a black hole, if you wanted to calculate the volume of it, then we'll just do a kind of a surface integral around the outside of the black hole. So that's the kind of thing that we're doing one dimension down with Green's theorem, is we're calculating, for example, an area or some other surface integral that, you know, at least nominally, it sounds like it requires getting into the interior of the region, but instead we can actually just compute it around the boundary of the region, can compute something else by going around the boundary. And I'll show you more applications today too. Okay, so yes, the key, well, you got to learn the statement of the theorem. The statement of the theorem is that a certain line integral is equal to a certain surface integral. And exactly how you're going to use that will depend on context. Sometimes you'll be given a line integral and sometimes you'll be given a surface integral. And sometimes you actually are given kind of none of the above. So let me start off by doing some examples with you. If my hardware will cooperate. All right, is that good? So it's a little cloudier today. I'm hoping that that will mean the lighting is better. So today is, oh, happy Star Wars Day. May the 4th be with you. Okay, so Green's theorem, let's write it out first to make sure we understand what it says. And it tells us that an integral of one kind of dimension matches an integral of another kind of a dimension. Specifically, if you have a closed curve C, so, you know, I usually draw just a little path, but this time I'm going to draw a closed path and call that curve C. And you notice I put a little arrow on that because it's necessary to talk about the orientation. As long as your path and your line integral is computed over a closed curve, then the integral of any vector field around that curve can be computed as an integral over the interior surface of that curve. I'll call that S now. So S is the interior. And I want to do a two-dimensional integral, or just dA. Maybe dA is a better notation. But the thing you're going to integrate will now be this kind of funny mixed partial derivative, partial of take the coefficient with respect to the coefficient of dy and differentiate with respect to x, and then the other way around, the coefficient of the dx and you differentiate with respect to dy, and you subtract those two. So that's Green's theorem. All right, so Malik's question is, yeah, well, what the heck, what is it good for? And, well, like I say, sometimes you'll have one of these and the other one will look easier. So that does happen, for example, in situations where your vector field is a gradient field. So let's see what happens in there. I'll use a different notation sometimes for this vector line integral on the left. You know that I can write this integrand here in other kinds of notations without changing the curve on the bottom. You know that you could write this, for example, as f dot ds, where this would be typically in boldface. So you think about vectors, where a capital F is now the vector field whose two components are P and Q. Oops, like that. So here's one application. Now this will be one that you already have learned about. It's going to be the fundamental theorem of line integrals. So I'll put this as a separate theorem for you. It's actually a corollary, a fast corollary of Green's theorem. I'll actually show you how you can use Green's theorem to see this. If your vector field is actually a gradient vector field, if it's the gradient of some other scalar valued function, then anytime you take such a line integral around a closed path, you're going to get 0. And the reason is very simple, because when you tell me that capital F is a gradient vector field, you know what it means to be a gradient. The gradient of little f would be the vector field whose two components are the partials of little f with respect to x and y. So here's your proof. Under this assumption, the p and the q will respectively be the partial derivative of little f with respect to first x and then y. That's how a gradient is computed. And if you put these two quantities now into the right-hand side, then, well, the thing you have to compute is the partial with respect to x of the second component minus the partial with respect to y of the first component. But our theorem on the mixed order partial derivatives says that these two second derivatives of f will be the same. And so the function that you're integrating on the right-hand side is just the function that's identically 0. So obviously the integral will also be equal to 0. The right-hand side of Green's theorem is just going to give you a 0, and that's the end of the proof. There's the symbol for end of proof. So in doing line integrals for a general vector field can be hard. Generally speaking, you have to parameterize the curve and so on. But if you know something special about your vector field, then you can bypass all of that because you already know what your integral is going to be. And before you say, yeah, well then, I mean, just getting a lot of zeros is not interesting, let me point out a corollary to this. A corollary means a theorem that you can prove really fast after you've already proved another theorem. So here's the corollary. If, again, sticking with the case where your vector field is actually the gradient of some other scalar valued function, then when you compute a line integral, not necessarily over a closed curve now, if I ask you to compute a line integral of this vector field between any 2 points, So there's a curve, and it joins 2 points that I'll call, I don't want to call them P and Q, call them A and B. Oh, look, A, B, C, look, that's good. Then you know that this is something that you would be interested in general in a physics problem if you have to, when you compute this line integral of a force along a curve, you're computing the amount of work that's done on the path from A to B. And in general, you know that this requires computing a parameterization of the curve. So it feels like you're not always going to get a zero. Obviously, you do work to lift a payload from the Earth to the Moon, for example. However, this constraint on the vector field does tell you something. The answer is that this integral will be the same as a line integral that you can compute of exactly the same vector field, but over any other path that joins the 2 points A and B. So I'll have, can I call this curve C2 or something like that? It has no connection at all to the previous curve, except that it starts at the same point and it ends in the same point. So this is called path independence of your line integral. It's not true for every vector field. Don't read too much into this. But this is a statement that's true whenever your vector field is the gradient of some other scalar valued function. Now we had this corollary before, just like we had the fundamental theorem of line integrals before. Well, I guess we called the two of these together as that fundamental theorem. The terminology we used before is to say that capital F is a conservative vector field. And then if you actually know what this scalar valued function is, you can even compute this integral very quickly. You know that it's going to be f of b minus f of a. So I use the language of saying the amount of work that you have to do, that's the amount of energy that you have to add to the object. You have to give it more potential energy if you want to lift a payload up. But the amount of work that you do is just found by comparing the potential energy function at the beginning and the end. So you know this in the cases where you do have a potential energy function. In the cases where the force that you're fighting really, well, it only depends on the endpoints. But that's the conclusion in general, is that your path is kind of irrelevant when you have a vector field like this. And the reason for this corollary is it's easy to see, can I just say since, if you take the left-hand side integral minus the right-hand side integral, well, that means you're taking the integral from A to B along this Kirby path, C, that I was given in the first place, and then to subtract the integral on the right-hand side, you know that that's the same as adding the negative of this integral. But the negative of this line integral is exactly what you would get if you kept exactly that path, but you parameterized it backwards. So go ahead and parameterize this one backwards. That would take you from the point B to the point, back to the point A along the same curve C2, but parameterized backwards. I drew a little arrowhead in there. I don't know if you can see that. But now you've gone from A to B and then back from B to A, so you've got a closed loop. You have a curve like this one. And since I asked in the beginning that you do this for a vector field that is conservative, it's the gradient of some other scalar valued function, well then, now that you're integrating over a closed loop, that interval is going to be a zero. So if the difference between the left side and the right-hand side is zero, that means those two integrals are equal. So this is a very useful thing. It kind of frees you from having to parameterize the original curve. You can parameterize any path from A to B. A straight line is usually the easiest one. And you won't get a different integral. In fact, you can generalize that same idea a little bit to cover the case of vector fields that are not necessarily even conservative. So let me say it this way. More generally, anytime you take any vector field F and any curve, any a curve C, and somebody says, hey, please compute this line integral for me. Well, with this generality, you can't expect anything too simple. You have been told how to compute these. You have to begin by parameterizing the curve and so on, and that's just a pain in the neck. But you can do something very similar to what I said over here. You can, let me draw the curve with its beginning and ending points A and B. You can always replace that curve with another curve that goes from A to B. So I'll call it C2. It doesn't have to be a straight line, although that's usually easier. You have to integrate the same exact vector field. However, you can go along a different path. You won't necessarily get the same integral, but what you will get will be two integrals, and I know how much they differ by. They're going to differ by the integral of this partial of q dx minus partial of p dy dx dy, integrated over the following region. I want you to have this original path C on one side and the reverse of this path C2 on the other side. And on this integral, I don't care about the direction in which you traverse this, because this one is a surface integral, so you'll just integrate this one over the interior of that region. And the reason for this kind of a formula is, again, the same as what I said in the previous one. If you calculate the integral of the left-hand side minus the integral of the right-hand side, now that will be the integral over the closed loop that starts along the curve C and comes back along the curve C2. And then you use Green's theorem to rewrite this line integral now. Since you now have a closed loop, then that line integral can be rewritten as the surface integral by Green's theorem. So this starts to show that Green's theorem is really very powerful, very useful. Any line integral, you can always compute it over any path that you want that joins A and B. You will have to put in a correction term, but that's a correction term that you can calculate using, let's say, Fubini's theorem. You have some partial derivatives to do. Maybe you'll get lucky and it was a conservative vector field, so this integrand over here might be the zero function. But even if it's not, I mean, it's just a surface integral. So let me show you an example of that, and I'll have to warn you, I'll show you some things that you have to watch out for. So let's have a vector field that's not going to be conservative. Let's just suppose that my vector field, is going to be x plus y comma x squared. And let me give you a curve over which I want you to compute this line integral. So suppose that I ask you to start at the origin, go 1 unit to the right, and then after you get there, go 1 unit straight up. So I'll put arrows in here to be clear that that's the direction over which I want you to compute this integral. So in the physics terms, you would imagine that this is I can draw little arrows for you at each point in the xy plane. Let's see, this one would be here, for example. So you would get a different little arrow at each point, and then you've got some force that you have to fight, and or it's acting on you perhaps, and you want to find out how much work is done on you to make you move first this way and then that way. And it's a line integral. So the work that's done would be an integral of this vector field integrated against this path. So here's the curve C that I had in my previous illustration. But that, at the very least, you can see that this is going to require 2 separate stages of calculation. I'm going to have to parameterize each one of those legs separately. And it's not at all hard in this particular case, but this would be an example of a curve that you dislike. And instead, we're going to replace it with a curve that I do like, so I can use the straight line path. This would be my C2 now. And the theorem that I just gave you said that if you want to go along the straight line path, go right ahead. You still have to integrate the same force field against the force field, I mean. But there now will be a correction factor. That'll be the integral over the triangle, the interior of the triangle of this thing that I keep writing down. And I'm going to change the notation in a minute, but let's keep this one. So we do an area integral of this function of two variables. Okay, so there's still a line integral to compute, but I can easily parameterize the path that takes me from the origin out to 1, 1. I would perhaps use this. Let's use phi of t to be just t, t. Now, that's where I want you to be at time t. At time 0, you'll be here, and at time 1, you'll be there. So take t in the interval from 0 to 1, and you'll parameterize that path in the appropriate direction. So now I can compute the line integral that's shown here in one step. You just integrate as over the interval from 0 to 1. Your integrand will be now the dot product of this, the values of the vector field that you're going to encounter. So that'll be a 2t in the first component and a t squared in the second component. And then you need to take the dot product of that with your velocity vector, which is obviously 1, 1. So the only function you have to integrate is 2t plus t squared from 0 to 1. And any calculus student can help you do that. The antiderivative is t squared for this part and a t cubed over 3 for this part. So there's that line integral. That's this expression here. I've just evaluated this line, the line integral that shows up on the right-hand side. I still have to add in this correction term, though. So let's see, how would I evaluate this surface integral? Well, first let's figure out my integrand. I need the partial of partial of q with respect to x minus the partial of p with respect to y. So I'll get a 2x for this part, 2x for this part, and just a 1 for that part. So it's a 2x minus 1 integrated with respect to x and y. And at this point, I guess I would use Houdini's theorem. Oh, sorry for the blinking camera. So I seem to have y on the outside. That's fine. My y coordinates go from 0 to 1. And for every fixed y coordinate, my x coordinates go from 1 to 1. Wow. Hang on about the camera. Let me plug it in differently. Sorry about that. Let's see if this helps. It usually does. So integrate with respect to x, and you will get your antiderivative is, oh, here, 2x minus 1, dx, dy. Your antiderivative on the inner integral is x squared minus x. When you evaluate it at the two endpoints, you have 1 squared minus 1, and then y squared minus y. And now integrating with respect to y, I'll get minus y cubed over 3 plus y squared over 2. Evaluated at 0 and 1 will give me 1/2 minus 1/3 is 1/6. So that's this surface area integral, surface integral. You add it into the line integral that I've already computed. So 4/3 and add 1/6. So 8/6 and 1/6. This should be 9/6, which is the same as 3/2. But I didn't actually ever have to compute it because I'm using Green's theorem to rewrite my integral by changing my path. Yes, the most ideal situation is where that's equal to 0, but even if it isn't, doesn't matter. We have a way of dealing with it. All right. Now, I did say there's something you have to be careful of. If you watched how I got this kind of a conclusion, you notice that I was using Green's theorem on the difference between these two line integrals. That difference between them means taking one of the line integrals in the direction shown and taking the other one in the opposite direction. And that will give you a closed loop. In order for that to match the surface integral, by Green's theorem, it has to be true that the net closed loop that you've just created goes counterclockwise around the region. So it's important in this case that it be this curve, C2, that shows up on this side, and the original one is got to be on the left-hand side. If you had to compute a similar example like this, if I asked you to compute the same line integral, same vector field, but with this path for C, if that's your C and you decide to replace it with this C2, well then if you take the original integral minus the integral over the new path, you'll have gone around the triangle clockwise instead of counterclockwise, which isn't, I know how to deal with that, but you do have to remember to put in a minus sign in that case. So this time the integral over the curve C will be equal to the integral over the curve C2 minus the surface integral over this triangle. Okay, and I won't write in the integrands because they're the same as the previous theorem. So you can deal with it, but you do have to be alert. You have to make sure that that your closed curve that you're creating comes from subtracting the appropriate curve from the other curve in such a way that you're going around the boundary of your region counterclockwise. Or if you end up going clockwise, remember to put in a minus sign. Okay, comments or questions on that? All right. Well, I'm not sure exactly when Green proved his theorem. I believe it was early in the 19th century, but don't quote me on that. Some point later, people realized that they could generalize this. Now, I've been telling you guys that these theorems all come in a family of similar theorems. The fundamental theorem of calculus was our starting point, and now we have Green's theorem. If you state Green's theorem in the right way, you can start to see it as just a special case of the next one, which is going to be called Stokes' theorem. So the change that I want to make is to say, your vector field that you have pointing in the xy plane can be thought of as a vector field that points in three-dimensional space. Just put in a 0 as a third component. Now this is something that's defined, this is a vector field defined on the plane, or if you like, you can say that this vector field is defined everywhere in three-dimensional space. So I'm thinking now of the same function f as being defined on all of R3. I mean, every point in three-dimensional space has x and y and z coordinates. You won't see any z's mentioned here, so don't bother putting them in. You evaluate this vector field, these three components, by just using the x and y components. Those of you who are thinking geometrically, you're going to take this point in three-dimensional space, just project it straight down onto the xy plane, and evaluate this vector, which will also lie in the xy plane because it's got a 0 as its third component. So if you actually draw such a vector field that has this constant of a 0 in the back as the third component, what you would do is you would draw your little picture of all the arrows in the plane and just make carbon copies of that at all the different levels into three-dimensional space. So it is what the fluid dynamics people call a laminar flow. Every droplet of water in this flowing, pool of water is staying at the same height above the ground. It could be moving more east-west or north-south, but it's not moving up and down at all. All right, why would I do that? The reason why is because this vector field now, if you think of it as a vector field in R3, then there's another vector field that we have talked about, which is the curl of this vector field. If you remember how the curl of f is computed, this is one of the notations we have for this, curl of f. This notation is supposed to make you think of how to compute the curl. You're taking this gradient symbol, which is treated as this vector. It's the partial with respect to x operator, and then the partial with respect to y operator, and the partial with respect to z operator. And you're taking the cross product of that with this vector, p and q and 0. And so that has several components to it. So the first component of a cross product, you may remember, you take the second component here and put it next to the third component there, and then subtract the order the other way, the pairing in the other order. So this would be taking the partial derivative with respect to y symbol and putting it next to, well, the 0 function, minus the partial with respect to z goes next to the p function. So that will be the first component of this cross product, and then there's two more terms to worry about. Well, I'll skip this one because it'll be very much like this one. I'll just draw your attention to the third component. The third component of the cross product is likewise, it's the first component here times the second component here minus the second component here times the first component there. Partial of the 0 function is always 0. This partial is also 0 because p was a function that only had x's and y's in it. So taking the partial with respect to z is meaningless. I mean, it's not meaningless, it's just kind of pointless. So you get a 0 there and a 0 there. And what you have for the third component is exactly the thing that I asked you to integrate on the right-hand side of Green's theorem. So if you like, you can rewrite Green's theorem by replacing that right-hand side by saying, oh, well, that's just the curl of f, or maybe you should decorate this f somehow to indicate that you've changed it a little bit to pop it up one dimension. You just threw in a 0 to make it a three-dimensional vector field. But that's okay, at least if I just saw it written this way and somebody asked me to take the curl, I guess I would instinctively say, well, this is the only thing that you really have to compute because the other two are zeros. So I wouldn't mind if you wrote Green's theorem in this form now. You take your vector field in the plane and somebody asks you to integrate this along some curve that's in the plane. I got to put a little arrow on it for a properly defined line integral. So if you guarantee for me that this is all this stuff is in the plane, both the vector field and the curve, then I guess I wouldn't mind if you just, oh, I'm sorry, it has to be a closed curve for Green's theorem. Then I guess I wouldn't mind if you said, well, I'm going to go and compute an integral over the surface that has that curve as its boundary. So call that S now, I guess. And what you're supposed to integrate, previously I've written out all these symbols, but now it's okay with me if you just write, oops, curl of f, and say I'm integrating that function of two variables over this region. Take the area integral over this region. That's fine notation just between you and me. But if you want to be precise, what you should say is, yeah, the curl of f, after you kind of artificially pop it up one dimension, the curl of f is a vector, and all I really want is the third component of that vector. Well, you can recover that third component by writing this as the integral of the honest-to-God curl. So you want me to put a little arrow over this somehow to remind you that that's a vector? And then dot that with the vector 0, 0, 1. And now you have a scalar valued function. This is a vector valued function, so is that. And now the dot product of the two vectors is a scalar. So integrate that scalar valued function over this set S. And, I mean, I guess I could have done other things here. I could have put anything I wanted in where those two zeros are, because when you take the dot product of this vector that's got a couple of zeros, well then, you know, all those terms will drop out. But I wanted to write it as 0, 0, 1 for a reason. The vector 0, 0, 1 points somewhere in three-dimensional space. Namely, it points directly up from the xy plane, which makes it perpendicular to the xy plane. So this quantity here is a unit vector that's perpendicular to the surface over which you're doing the computation. I mean, the surface was supposed to lie inside R2 in the first place, so you don't ordinarily need to think about it as R2 being a part of R3, but why not? Because we've talked about surface integrals. So here we have exactly the kind of notation that we have seen in the past, where somebody hands you a surface, flat or otherwise, and they ask you to compute a surface integral, the kind of surface integral that you get from a vector field, namely specifically this vector field. You take the dot product of that with your unit normal vector, and then you compute the integral over the surface. And now that I've started to remind you of that language of surface integrals, I'll remind you another way we wrote that. You write out the name of your vector field, and I'm going to stop putting these little arrows over the word curl in a minute. And then instead of just using the letter n all the time to talk about the normal vector, you simply put a dot and then ds, where this was also written in boldface, or somehow you indicate that that's treated as a vector. So this is nothing but a different notation, a variant notation for what people have in mind when they said to compute this one. And you're integrating that, all of that stuff over this surface. This is the surface whose boundary was that curve in the plane in the first place. So this is a long way of saying Green's theorem is a perfectly innocuous theorem about vector fields in the plane, line integrals against that vector field around closed curves in the plane, in the plane, in the plane, in the plane. But, you know, you can recognize it as being something that actually would make sense even if this surface were not in the plane, even if the curve did not lie in the plane, or the vector field didn't always blow things just across the plane. And if it makes sense in a larger context, you might wonder whether it's actually true in the larger context, and it turns out the answer is yes. So that'll be Stokes' theorem, and I'll explain that in a second as soon as I take this question. Who's asking a question? Malik, you have a question?
Yeah, so I was just wondering, you said in the second or third step on the first page, you said that the curl of F, or between those two, it says curl F, and then I think it says curl A.
The curl, oh, yes, I don't know where that A came from. I have no idea where the A came from. I'm sorry.
And then I was also wondering, like, the dA, is there a reason why you changed the dA to ds?
Yes, I did that just to be consistent with the book. The book seems to like to always use the letter capital S in the name of its differential for surfaces. I don't. You guys have heard me over and over say, look, when you're computing a surface integral, you know the spirit of this, right? You're going to chop up the surface into little bits and then multiply the area of each bit times this dot product, this scalar valued function. So it seems to me if you're doing areas all the time, you should write a capital A, but I guess it's for historical reasons, people put a capital S in that spot. So it is a notational thing. You are welcome to use a capital A consistently if you like. Does that answer your question?
Yes, thank you.
Yeah, I'm glad you caught me, by the way. I don't know where the A came from up there. Those should have been all references to F. All right, so here, let me state Stokes' theorem. By the way, he was not named Mr. Stoke. He was named Mr. Stokes. So it's two S's in there. Stokes' theorem. And he says the following, if S is any surface in R3, then let the C be the boundary of S. So I've used this notation with you guys, I think last time or the time before. So again, what this means is, in a word, it just means the boundary of S. And that'll be a curve, but specifically it'll be a curve that has an orientation. And that orientation would be derived from the orientation that you have on the set S. So there's a little complication here for directions, orientations, and that'll maybe mess you up with a minus sign. So I'll fix that in a minute. But then here's what Stokes says. If F is any vector field on R3, then when you integrate that vector field, you calculate a line integral of F on this curve C, on the boundary of the set S, you will get the same answer as if you had computed a surface integral over the surface S of, well, I'll just write it this way. Sorry, I'll write it this way. It's curl of capital F dotted with ds. Now, this is what Malik was just asking about. I guess I would say capital DA. The book likes to put it as ds. But I can actually avoid both of those notations by reminding you guys that what this means is when you are asked to compute an integral over a surface of a function that comes from a vector field, and your clue is that there's a vector field that has been mentioned. The curl of our original F is a vector field, and you see a dot that says that there's some dot products going on, and typically this would be written in boldface as well as the vector field that you're integrating. So you know a different notation for this is that you're going to walk around the surface capital S, chop it up, take the area of each piece and multiply the area of each piece by the following scalar valued function. You take the vector field that was handed to you in this integral and you take the dot product of that with the unit normal vector. Now, there are a couple of things you should notice. First of all, in the special case where the surface just happens to lie just on the flat XY plane, it happens to sit inside three-dimensional space, and if then its boundary would also just be, you know, a curve in that plane. If your vector field also just happens to be directing points in the plane with vectors that have a 0 as their third component, then what I've just written down here is exactly Green's theorem. So Stokes' theorem includes Green's theorem as a special case. It's the special case where the surface is flat on the bottom and where the vector field is just pointing along the XY plane. So that's what I was doing on the previous page, was to show you that this thing contains Green's theorem. Green's theorem is a special case of Stokes' theorem. But it is more general. This covers all kinds of surfaces that float around in three-dimensional space. And what that's going to mean for you is you might be off the hook if I ask you to compute some sort of a surface integral. The only catch is you can have any surface you like. You'll be able to turn this surface integral into a line integral, but only if your vector field, the one that I hand you when I just say, hey, compute a surface integral for me, your vector field has to be the curl of something else. And that's not true of every vector field. Not every vector field in three-dimensional space is the curl of a different vector field. And even if it is, it can be a hard job to try to figure out what the original F was if I just give you this one. So it isn't a panacea that's going to help you avoid calculating those surface integrals, but it can be useful in some circumstances to turn one of those into one of these. On the flip side, you might think of this as a recipe that helps you not have to compute line integrals anymore. And there again, I say, well, maybe, because you can have any vector field now. You can have any curve wandering through three-dimensional space and any vector field with one little caveat: your curve has to be the boundary of a surface. And in particular, that means that your curve is going to have to be a closed curve. It has to come back to where it started. So Stokes' theorem can be used to transform away any line integral, the line integral of any force field, but only if you're integrating around a closed curve. Now, you can address that and still use Stokes' theorem the same way that I used Green's theorem to help me evaluate line integrals that were not over a closed curve. What it did in that case is it told me that I could replace one curve with another curve, and I'll show you some examples of those. So how you're going to use Stokes' theorem is not always clear, but it is another tool in your arsenal. It'll tell you that this one-dimensional integral will match that two-dimensional integral. This one's not completely general because you're restricted on the curve, and this one's not completely general because you're restricted on what kind of vector field you might be integrating. Okay, one thing I do have to say, though, is I have to talk to you about the orientations of these things. To do this, I have to remind you that in order to calculate a surface integral, somebody has to tell you which of the two possible unit normal vectors you want to use at each point on your surface, right? There's always the two that point in opposite directions. And the surface integral doesn't really make sense until somebody clarifies which one do they want. Do they want the upward normal or the downward, the inward one or the outward one, however they want to describe it. In the same way, the line integral doesn't really have a meaning until I tell you which way to go around this loop. This is going to be a closed curve, but should I parameterize it that way or that way? And don't tell me it's supposed to go counterclockwise, because that word doesn't have meaning anymore. If you imagine two people that are sort of, they've come together and they want to talk about a line integral around a curve, and that curve is like a hula hoop that's in front of both of their faces. If I ask both of those people to trace out what does it mean to go counterclockwise around the curve, this character would be saying to go that way, and this character would be saying to go that way. So they would actually be going opposite each other. I can't do my fingers opposite. So in order for this theorem to be correct, you have to have the right understanding of which is the orientation of the curve that matches the orientation of the surface. And that's most easily understood with a picture. If this is your floating surface in three-dimensional space, so that's capital S. When someone asks you to compute a surface integral, they must have in mind, I mean, the kind that comes with a vector field, they must have in mind one of the two fields of normal vectors to choose from. So the way I've drawn this particular one, you think of it as a kind of a blanket that's floating above the XY plane. So in one word, I would describe this as the upward pointing normal vector. I mean, you want to vary your normal vector will vary continuously as you wander around the surface, but you want to have it vary smoothly. You don't want to choose the upward one here and then suddenly the downward one. Okay, if you've been given the surface and an indication of which normal vector is of interest to you, then you have to figure out which is the right direction to walk around this curve. And the answer is you should do it standing on the surface with your head up. In other words, you want the vector that goes from your feet to your head to match the normal vectors that you're encountering right here along the edge. So that may be up or it may be down. And I mean, exactly whether it's considered up or down might vary with the surface. Imagine the surface kind of wraps around like this. Okay, and somebody says, no, I want the normal vector that points like this. And then over here, it starts to bend that way. And now it's pointing that way. And at this point, it would be pointing actually down. Well, that's fine. I still want you to walk in such a way that as you go along the boundary, your head is up in the sense of matching the arrows. So by the time you get here, how do you draw a person upside down? By the time you get here, your head would actually be down. As you do that, stick your left hand out. And I want your left hand to be pointing to the interior of the surface. So a person who walks along the edge this way, as if they're facing in the direction of the little arrow here, and their head is upwards, meaning the way the arrow points, then their left hand would be pointing towards the surface. And by the time they get up here, they'll still be walking along the curve this way. Now this person has become a fly on the ceiling. So you have to kind of use your 3D imagination to understand where their left hand is. but their left hand would be pointing, well, in that direction more or less. It would be pointing into the surface still. So that tells you which of the two directions to use on the curve if you've been given the orientation of the surface. And on the flip side, if you already were given a curve, then you have to choose the orientation on the surface to match. So can I just say, on this boundary of S, on the curve that's called the boundary of S, use the orientation of the curve that matches, mathematicians would say it's induced by, that matches the orientation, meaning the normal vector, that's on the surface, capital S, and it matches it in the sense that as you walk along the surface, here's the surface, and here's you want to walk in such a way that the normal vector is pointing from your feet to your toes, from your feet to your head, and your left hand, which I put left and right, your left hand is pointing into the surface, so your right hand is sticking out over the edge. All right, so that's the statement of Stokes' theorem, and I hope you can see that it has the same feel as Green's theorem, and it generalizes Green's theorem, but the applications of it will be, well, just like I got some applications for Green's theorem, except now I can do it for all kinds of floating surfaces. And, well, I guess since I'm out of time, I'll postpone that until Wednesday. Do you have any questions you want to ask before we freeze this here? All right, give it a shot. Try some more of the homework problems and ask me about them on Wednesday. Make sure you understand, well, you better remember how to compute the curl, how to compute line integrals with vector fields, how to compute surface integrals that come from vector fields, and also make sure you understand how you get the orientation. Okay? Oh, Malik, go ahead.
Yeah, I was just gonna say, does this like in dynamics we had learned, like we had defined the normal unit vector as the vector that like points towards the center of curvature of like the path or the, I guess, the surface. Would that be consistent with this definition? Or?
Yes, but in my the way I'm describing it here, it doesn't matter which of the orientations you choose. So if for example S is the surface of the sphere, then you could take the inward pointing normal or the outward pointing normal. They both work just as well in terms of the but well, actually let me do not the whole sphere because you'll be confused by something, but let's just do the upper hemisphere. If somebody says, I want you to compute a surface integral with some vector field, so calculating some flux that's going across this sphere outward, so there's your normal vector now. And if the surface is the upper hemisphere, then the boundary is the equator. If this is the northern hemisphere, the equator is along the bottom. So there's your curve. But you need to stand on the surface in such a way that the normal vector goes from your feet to your head. So a person could start at the North Pole standing on the top of the globe, and then they have to walk down to the equator, but they'll still be with their head has to be pointing to the outside. And then for such a person, if they wanted to walk with their left hand pointing sort of into the surface, then they would be required to walk this way. If they were to walk the other way, I invite you to grab a globe and actually try it. If you try walking the other way, then as you face forward, it would be your right hand that's sticking into the surface. Now, you could have the inward pointing normal, I don't care, that would point to the center of curvature, center of the sphere. But then that would require that you be walking along in the opposite direction along the hemisphere.
Okay, that makes sense, thank you.
Alrighty, guys. Oh, go ahead, another question?
Sorry, can you go back to some, I didn't quite catch everything you were talking about with conservative vector fields and gradients. So I don't know if you maybe could just show those notes.
Certainly, let's go back to that. So I didn't spend too much time on them because we had already actually, like weeks ago, years ago, it feels like, we were discussing these conservative vector fields. So let me put that into this context. So conservative vector fields are those capital F's that come from the gradient of some scalar valued function. The terminology of, I don't know why the terminology of conservative is used, but it means that your force field actually has a potential energy function, little f, that's associated to it. And then what this corollary says, that under those circumstances, when you want to figure out how much work is done, that's what this line integral computes. The line integral of this vector field along a path that goes from a point A to a point B, the path doesn't matter. You can have a different path as long as it has the same beginning and ending points. When you compute the line integral over a different path, you'll get exactly the same number. And in terms of conservative forces and so on, that makes sense, because when you talk about the amount of work that's done, you guys probably know from your physics classes that you calculate the amount of work done by simply comparing the potential energy function at the beginning and the end. It doesn't matter what path you use to fight gravity. That's the ancient Egyptians figured that out, that even when you want to move that heavy block to the top of the pyramid, the amount of work that you're going to have to do will be the same, whether you choose to have the zigzag path that goes along the outside of the pyramid or just straight up the side of it. Of course, you would feel a stronger force. You have to apply more force to the block to move it the long way, but the force times distance is actually going to be the same. That's the work that you do.
So what is LHS and RHS?
Left-hand side and right-hand side of this equals sign.
Oh, okay.
If you take so if you take the line integral on the left and you subtract the line integral on the right, then that's the same as taking this line integral plus the same line integral here, indicated here, but with that curve reversed.
So when you were doing the Green's theorem, where you added the area, so you did like a general line integral equals a simpler line integral plus the area, that was for a non-conservative.
Correct. I mean, you're welcome to use this in the case where the vector field is conservative, but in that case, that would be a zero.
Yeah, it would just drop away. So that's really only useful for non-conservative vector fields. Okay.
Right. I mean, I don't know, some of you guys just like to memorize lots of different formulas for different special cases. To me, I might just memorize this one, and then if I had a conservative vector field, I would say, oh, yay, that part is zero, so those two line integrals would be the same.
Okay. Yeah, fair enough. Thank you.
Honestly, I'm just going to remember Stokes' theorem. Every single thing I said today is a consequence of Stokes' theorem. Green's theorem is a special case. You can derive this one from Green's theorem. You can derive this corollary from that, etc. All right, good questions, but let's stop it there, and I'll see you guys on Wednesday.